We are going to solve a very interesting problem about the plane stress tensor, and I advise you to review videos number 21, similar matrix, 22, eigenvalues and eigenvectors, and 27, property of gradient. Now the problem is, given the plane stress tensor -6, -12, -12, 1, and the plane, there's the pi, there's in this figure there, whose n here is the normal, outward unit normal vector, t is the stress vector, point A is P0 and point B is 0P. P is a number, a real number. Okay, in the x1, x2 and x1, x2 coordinate system, determine the stress vector components, the normal stress sigma n, and the shear stress tau s relate to the plane pi. Now, you see, x1, x2 is related to the eigenvector, the principal direction of this stress tensor components that it's given right here. See, let's solve this problem. First, we're going to solve this problem in this x1, x2 coordinates. And then we're going to solve the same problem with x1 and x2 related to the principal directions of this matrix over here. The plane in the figure can be written by x1 plus x2 plus 0x3 is equal P. Now 0x3, okay, is represented, this plane is represented by this segment over here. This is a straight line. See this straight line over here in the plane. Now, it's obvious that for x1 is equal 0, x2 is equal P, so it's point B. That's point B, that's point A. For x2 is equal 0, x1 is equal P, so that's the equation of this plane. Now, using the property of gradient, you see, that's a function phi, so gradient of phi is perpendicular to the plane. Okay? So the normal to the plane is equal nabla phi, which is equal, gradient of phi will be, you see, partial respect to x1 of phi, x1 plus x2, E1 plus partial respect to x2 of phi, x1 plus x2, E2. This is equal. Now this is 1, this is 0, because x2 and x1, they are independent. So this will be 1, E1 plus E2. This is the normal vector outward. Now we want to work with the unit vector. So n is equal this normal vector divided by the magnitude of this vector, okay, n dot n. So n dot n, you see, this is 1, this is 1. 1 dot 1 is 1 plus 2, so this is equal n divided by square root of 1 plus 1. This is n divided by square root of 2. So n is 1, 1. You see, n is 1, 1. So this will be equal to 1 of square root of 2 E1 plus 1 of square root of 2 E2. So this is the unit vector as this is n. This is n over here. Okay? Now, let's continue. Now I want to find out the stress vector T, See? This stress vector T. Stress vector T, T1 and T2 are the component with respect to x1 and x2. N1 and N2 and N2 are the unit vectors, the component of a unit vector with respect to x1 and x2. And this is the given stress tensor. So this will be equal to, this is 1 of square root of 2, 1 of square root of 2. Now the matrix is minus 6, minus 12, minus 12, and 1. This is a symmetric matrix because the stress tensor sigma ij is equal to sigma ji, which means that it's symmetric. Now let's do this calculation over here. Then you're going to get T1 and T2. So this will be equal to minus 9 square root of 2 minus 11 square root of 2 divided by 2. So this is T1 over here. You see, this is T1, this is T1, this is a component T2, and this is T2. Let's keep this because now we are going to obtain sigma n, and the shear. So the normal stress and the shear stress with respect to x1 and x2 component. Now you see sigma n, I will draw here. See, look, sigma n is the component of T, the component of T here. See, this will be sigma n. Now if we do the dot product between T and N, we're going to get sigma n. So sigma n, the component, is the dot product of T dot N or N dot T because they are vectors. The dot product, you can permute the dot product, but you cannot do this if you have a second order tensor. This is not valid. Now let's calculate sigma n. So sigma n is equal, this is the vector n, you see? This will be 1 divided by square root of 2, 1 divided by square root of 2. See, this is n times, now a t, okay? The t, the stress vector is minus 9 square root of 2 and minus 11 square root of 2 divided by 2. So this is a very simple calculation. You see, look here, 1 of square root of 2 times this, you see the square root of 2 will cancel, so this will be, sigma n will be equal minus 9 minus 11 over 2, so I multiply this, okay? This is minus 29 over 2. Now, you see, if the dimension of the stress tensor is megapascal, this will be megapascal, okay? Depends on the unit. So let's keep this in mind, okay? Now, you see, look, here we have T, then you have N, see? Now you project T here, let's increase here. So this is T, this is N. So this here, this will be sigma N. You see now, you project, if you project here, this will be tau shear, okay, on the surface. Tau shear will be right here. So it will be this here, okay? Now this is sigma N, this is the shear stress, okay, on this plane here. So this will be equal to this. This is shear stress. So just apply Pythagoras theorem. So you see, the dimension, the magnitude of T is equal T dot T minus sigma n square, this is equal tau s square. You see, t dot t is a magnitude. You see, this here, the magnitude of this is t dot t, is the size. This is sigma n. So, from Pythagoras theorem, this will be, we can calculate tau s over here just using the rectangular triangle. See? Now here. Let's do this. Because you see, we have t here. You see? You have t in the components. You have t dot t, you can calculate. Sigma n squared is minus 29 over 2 squared. T dot t is the magnitude of t. Okay? Now, sigma n squared, this is minus 29 over 2 squared. So we can obtain the shear stress. You take the square root of this number here, then we have the shear stress. And to calculate tau s, see, look, this magnitude is t dot t, see, magnitude is squared. Now, sigma n is squared, look, this is magnitude squared minus sigma n squared is equal to tau s squared. So we have t, you see, t was calculated. Sigma n was calculated too. So let's do this dot product minus sigma n squared. So those are numbers. So for 468.56 minus 210.25. This is 26.31. The square root of 26.31 is approximately 16 megapascal. So let's write here. You see, all this calculation here is for x1, x2 coordinate. Let's repeat all this calculation now for the principal direction coordinate. We are going to calculate the eigenvalues. Then we calculate the eigenvectors. So this solution you can see in the previous video, you see, in which we had this matrix 5, 0, 0, 0, 0, and then minus 6, minus 12, and 1. You see, the previous video we just calculate. Now this one is just a plane. Okay, so it is minus 6, minus 12, and 1. So the eigenvalues of this, we can do, this is minus lambda, you see, 6, minus 6, minus 6, minus lambda, minus 12, this is 1 minus lambda. See, this is equal to 0. You see, you see the previous video, okay? You're gonna see this. So this is equal to minus, let's put 6 plus lambda, that multiplies 1 minus lambda. Now, minus is plus, so this direction is minus, so minus 144 is equal to 0. So this will come up to lambda squared plus 5 lambda minus 150 is equal to 0. So then we have lambda 1 is equal, sigma 1 is equal 10, and lambda 2, let's say sigma 2 is equal minus 15. In this case, you put megapascal, okay? Megapascal. That's easy. Now, for each lambda, we're going to calculate the eigenvector. So, let's say for lambda, for sigma 1 is equal 10, or lambda 1 is equal 10. Now, let's put here, see, look. You see, minus 6 minus lambda, you see, this will be minus 16, minus 6 minus lambda, minus 10, so this is minus 16. This is minus 12, this is 1, minus 10, so this is minus 9. See? This is homogeneous equation, A and B. This is equal 0. Okay? Exactly like we did before. So, you see, the determinant of this homogeneous equation, if you multiply minus 9 times minus 16, it will be plus 144. Minus 144, this is 0. So this, we have non-trivial solution. Non-trivial solution. Okay? Let's take one of these. So let's put here minus 12a minus 9b is equal to 0. So this is b is equal, 9b is equal, you see, now here will be minus 12a divided by 9, see. Let's put a is equal 1. So b will be, for a is equal 1, b will be, let's divide by 3. So this is minus 4, this is 3. So the eigenvector P1 will be, a is equal 1 over here, and this will be minus 4 divided by 3. See? Let's calculate now for sigma 2 is equal minus 15 is equal lambda 2. Okay? Lambda 2 is equal, sigma 2 is equal minus 15. So minus 6 minus 15 is plus 9. So this is minus 12, minus 12. Now 1 minus 15, so this will be 16. Now let's solve here a and b. See? Now look, and again, 9 times 16 is 144. Minus 144, this will be 0. So also we have here a non-trivial solution, you see, for the homogeneous equation. So let's solve here 9a minus 12b is equal to 0. See, it doesn't matter if you use the first one or the second one, it will be the same. So for a is equal 1, then we have 12b is equal 9. You see? 12b is equal 9 for a is equal 1. So b equal to 9 divided by 12. If divided by 3, it will be 3 divided by 4. So P2 will be, see, 1, and here 3 divided by 4. 3 divided by 4. So, but we want the orthonormal. You see, look, these two vectors, they are orthogonal. You see, if you multiply 1 times 1 is 1, minus 4 divided by 3 times 3 divided by 4 is equal minus 1. So P1 dot P2 is 0. You see, because the stress tensor, the matrix is symmetric, as we demonstrate in the last video. So let's calculate the unit vectors. So the unit vectors, now let's call V1. See, V1 is equal P1 divided by the magnitude of P1. Let's put here. See? What is the magnitude of P1? So this will be P1 divided by square root of P1 dot P1. This is equal, see, the vector P1. Now, P1 dot P1 will be, you see, P1 dot P1 is equal 1 square plus minus 4 divided by 3 square. So this is equal 1 plus 16 divided by 9. See? So this will be 9 over here. 9 plus 6 will be 25. So square root of 25 divided by 9 is 5 over 3. So this will be square root will be 5 over 3. So it will be 3 over 5 times P1. You see? 1 minus 4/3. This will be 3 divided by 5, and here 3 cancel, so this minus 4 divided by 5. So this is V1. Let's write down. V1 is the unit vector. So V1 is equal, now 3 fifths minus 4 divided by 5. Now let's calculate V2. You see? Now let's calculate V2. Now V2 will be P2 divided by the magnitude. V2 is equal P2 divided by the magnitude of P2. Now P2 is 1 and 3/4. Now let's get the magnitude of P2. So the square root of P2 dot P2. This is equal, you see, 1 square. That puts square root of 1 square plus 9 divided by 16. You see, 3/4 square is 9 by 16. So this will be equal square root. Here will be 16, and this will be 25. So this will be 5 by 4. So this is 4 by 5. That multiplies P2, 1 and 3/4. So this is equal, now 4 divided by 5. Now here 4 cancel. This will be 3 divided by 5. So we have the system x1, x2, like this. Let's put like this, okay? Look. This is the vector, this x1, and this is x2. And this is the unit vector, v1 and v2. See? That's the unit vector. Now we can calculate all the parameters, okay? Now first, n, t, sigma n, and tau s. Before that, please go eigenvalues and eigenvectors. This is x1, x2, and this is x1, x2 in Roman. Now, you see, look, this is minus theta. Let's put it here, minus theta. That doesn't matter, okay? Let's write down U1. Okay, from this picture, okay? Okay, now let's project V1, okay, on this x1 axis. So U1 will be cosine of theta V1, you see? Now U1, you see, will be V1 cosine of theta. Now, this is V2. When I project here on U1, it will be plus. So this will be plus sine of theta V2. Now let's project on E2 axis. You see, look, V1, you can see here that V2 will be cosine of this, okay, it will be plus, you see, the plus cosine of theta V2. You see, this is theta, this angle here is also theta. You see, let's project here. Now let's project now V1. You see, V1 will be in the negative part of V2. So there will be minus sine of theta V1. Then you have the matrix E1, E2. Okay, now there's a matrix, there's a column matrix. Now here is cosine of theta, sine of theta, minus sine of theta, and cosine of theta. See? V1 and V2. See? V1 and V2. Now, that's we call this matrix, transition matrix, as P. So, P minus 1, P, the inverse, is equal to the transpose, because we are dealing with orthonormal basis. So this is equal to, now, will be cosine theta sine theta. You see? The first row will be the first column. This will be minus sine of theta and cosine of theta. See? Now, we can see clearly, you see, that V1, 3 divided by 5 is cosine, this is sine in this case, okay? Cosine, this is minus here. So, this matrix over here, the P matrix, look, I can write like that. Look, this is the component 3, 5 minus 4, 5. This is 4 divided by 5 and 3 divided by 5. So this is my matrix P. You see, you compare right here. See? This is P minus 1. Now, P relates the component of x1, x2 into x1, x2. There's a Roman index, okay? Now, P minus 1 relates just the inverse, okay? For the P minus 1 act, for instance, in a vector n, okay? And give me the component of the same vector in this x1, x2, x1 Roman and x2 Roman. You see, that's what with P minus 1. That's what I want. I want to transform the component of this normal vector into the component of normal vector with respect to the x1, x2. This is just simple operations. See? Now, n star, the normal, the orthonormal, these components, you see, the vector, the normal is the same vector. It doesn't change. Please see similar matrix. Okay? Now, the component that will change. So, the component of the normal vector will be the inverse of matrix P applied to n. You see, this is n. You see the inverse. That transform the components in the x1, x2 into the components of the principal directions. So this number, just plug this number over here and multiply. So this is the component. We'll call n asterisk. Now, the stress vector, the component of the stress vector with respect to the principal directions will be P minus 1 or P transpose times T. So I have T over here. See, I have N over here. So just multiply P minus 1 or P transpose. This is the component of the same stress vector, but the components changed. Now, sigma n, you see, sigma n doesn't change. You see, look, if you have a surface here, you have T, you have N. See? The projection will be sigma n. You see? You can use any coordinate system, So this vector here, this vector will not change. So sigma n must be the same. So this is minus 29 over 2. On the same is tau s. Tau s is T asterisk dot. T asterisk, the magnitude minus sigma n. So, you see, this is very important. See, you can use any coordinate system, any. x1, x2, x3. Now, x1 prime, x2 prime, x3 prime. You see, any. See, the dot product will not change. You see, the components will change, but the dot product will not change. So this is the same. Tau s squared, you see, minus sigma n squared. This is minus 29 divided by 2 squared. These are those numbers, you see. Now minus this tau s squared. Will be all this number over here, which is exactly the same as we did before. so the square root will be like this. So these are the same, you see? Doesn't matter if I use x1, x2 coordinate system, or I can use the principal direction coordinate. Doesn't matter, see? Stress tensor, okay, T, let's work with T1, T2, based on x1, x2 coordinate system. Now, you see, do you remember? So T1, T2 is equal. Now, N1, N2. Let's work in the 3 dimensions. See, this is an observation here. T1, T2, T3. Now, N1, N2, N3 times, now, sigma 11, sigma 12, sigma 13, sigma 21, sigma 31, sigma 22, sigma 23, sigma 32, sigma 33. So, T1 will be, look, N1 sigma 1, N1 sigma 11 plus N2 sigma 2, 1, you see this times this, plus N3 sigma 3, 1. The same, T2, okay. Now, look, this is X. Now let's work in the principal direction. Principal directions. Look how interesting, you see, look. Then I have the same tensor, the stress vector here, but the components will be, obviously, the component will be different. Now, here, this is equal, look how interesting, look, N1 asterisk, N2, and N3 asterisk. And the matrix will be simpler because here is sigma 1, 0, 0, 0, sigma 2, 0, 0, 0, sigma 3. Let's expand this. You see, this will be N1, sigma 1. You see, this is T1. Let's put this, look, equal. Let's put here. This is N1, T1. You see, we avoid this calculation over here. So T2 star will be N2 sigma 2 and N3 sigma 3. You see? Look, very simple. This will be T1 star, T2 star, and T3 star. And all the results using this system or using X1, X2, all the results will be the same. So now, if there is a topic in which we maximize or minimize tau s, you see this is equal T dot T minus sigma n squared. Look, if you minimize this function here using x1, x2, x3 coordinate, okay, you see, you'll be, I don't say complex, you see, but is a lot of terms. Now, if you want to find out which n is such that tau s is maximum or minimum, you see, you just use the principal direction because, you see, T1 is simpler, T2 is simpler, T3 is simpler. And the result will be the same because it depends on the coordinate system.